Okay, so here's just a short follow-up from previous episode where I showed you how to build this small electric jet. There are some things that I think I forgot to tell you, and that's the size of the disc magnets that I use. They are 10 millimeters diameter and they're 2 millimeters wide, and the bearings in the rotor are 6 millimeter outer diameter and they are 2 millimeter inner diameter and they are 2.5 millimeter in height. You can get them from for cheap on eBay. Okay, so I thought that, well, there were many comments about me not having properly designed the parts, and I sort of agree. The first version is constructed in such a way that the rotor was actually just completely flat, and it mated to the stator just like this, and there were no seal at all between the halves, so there was a lot of air coming out from the sides as well as from the back. So I have corrected that in the design I'm going to show you today. So I have there's a small notch there on the rotor, and it sits in a groove in the circumference of the stator, so it creates a much better seal in between them. So it fits, it slides on something like that, and in the best of days you can make it to spin freely and still have a fairly proper seal. And I thought that I would do some measurements for you, because I know, of course, since it looks like a jet engine, you do want to know how much thrust it produces, and it's not supposed to be a propulsion unit for a radio control plane or something like that. It is a project about three-phase electric motors, and how you can construct simple pancake style. There are axial flux style motors, and the reason for me to make this a radial fan is that I do want to have proper cooling of the coils, but also you can get a small amount of thrust out of it as well. So it's just a nice looking educational project. Okay, so let's look at the design changes I made. The first one here, you can see this is the inside of the stator housing. This is the coil carrier, and it has 3 static vanes, and the rotor looks like this. It's sort of a radial fan that goes over, well, it's quite radial all the way, like that. And the ball bearing sits in there, and on the other side I have not taken away the support material here yet. The new design, I have a coil carrier, a stator, with twice as many blades to unrotate the airstream, to straighten out the airstream. And the rotor, you can see it's more of a radial fan up here, and it converges to a more like a steep propeller blade. And it's also slightly wider, the blades, so you simply have more throughput through the system. So as it rotates, the swirling airstream is straightened out by the stator blades, and the coils are in between, and you have the magnets sitting on the rotor. So it's a slightly higher throughput in this setup, and these parts are so fragile without the housing. So as soon as you print them out as complete whole parts, the stator blades and the rotor blades are fused to the outer structure, so they're much more resistant to mechanical stress. Okay, so let's do some measurements and some tests. Here's my crude setup. It's just an ordinary smoke machine, and we will be starting with trying out the original motor with its relatively huge gap. It is powered by a 3-cell lithium battery, 350 milliamp hours, and there's a servo tester as well. so that was the old design with the big air gap between the rotors. Now I have put the new design motor with a labyrinth seal, or close to a labyrinth seal anyway, with the same battery, and the coils inside the motors and the magnets are the same. So let's see how it performs and how much smoke comes out from the gap. I think that was kind of interesting. Of course, the old motor did leak in the gap, and the exhaust plume looked really divergent and weak. And the new motor with the better seal did leak a lot as well, but the jet exhaust looked much more contained and powerful. It will be interesting to see what thrust values these two motors deliver. Okay, so before we do the final thrust measurements, I just want to check how much current they draw at say 12 volts. That would represent about the 3-cell LiPo battery. I think they are good up to like 14, 15, 16 volts, but I think they will be sort of in a pain at those voltage levels. So let's start with the old motor, the first design. You can see the 0.06 amp current draw. I think it's a standby current for the servo tester and the speed controller. Okay, here we go. So that looked pretty much spot on, like 1 amp. And now let's change over to the new design. And that looked pretty much spot on, like 1.2 amps. And it seems reasonable that this new motor draw slightly more current, although the magnets and the coils are the same, because it's simply a higher load with the enhanced design, which can throughput more air. So it simply accelerates more air. Now let's see how much, or rather how little thrust these small motors can generate. Let's start to try the first version, the motor that does not have a seal between the rotor and the stator. It's zeroed out, so let's start. So just over 4 grams, 4.1. Let's try that again. Okay, so 4.2 this time, so somewhere in the 4 gram range. Now let's change the motors and see how much the new design can produce. Okay, so this is the second version, the motor which has a seal between the rotor and the stator. So it came in just shy of 7 grams of thrust, and the first version was around 4 grams of thrust. So it's not quite a twice the thrust in the new version, but it's pretty close. It does seem that the old version, or the new version, revs higher than the old version, And I'm not sure how that comes, because it's pretty much identical electric motors inside them, the 3-phase DIY motor. Okay, so let's try to sum that up. There is a significant performance increase going from this version, the first version, with the air gap in between the rotor and stator, to this version where you have a much better seal in between the parts. However, the new version does draw 20% more current, but it delivers almost twice the thrust, so it's still a very significant gain. But the big thing with these motors are that they are educational to build. It's interesting to learn about 3-phase brushless permanent magnet motors. They're so simple with 3 coils and 4 magnets, so you can reflect about how they function just while you're building them. You can gain a lot of knowledge that way. Another good thing is that they have such conservative current draws. The 1.2 amps is at 12 volts. At 9 volts it consumes less current, so you can actually power it with a standard 9 volt battery, which is kind of fun. So I can sort of blow my hair. You can hear here from the microphone, the airstream. And someone kindly suggested as well as I should wear safety goggles, and of course you should wear safety goggles. However, I have tested the motors to the point where the magnets exits the rotor, and it's almost twice the RPM here compared to this setup. I will just show you that clip as well. So we're up to 15,000 RPM now, 16,000. 20, 25, 30,000. It's not very well balanced, but here we go. Yeah, so that is what happens when your magnets come loose. So make sure not to over rev this motor. I think that was about 35,000 RPM, and let's see here what's left of it. Well, the magnets have left the rotor, so that's bad. Okay, so until next time, stay safe.